Hey, today we're starting the applications of logs and exponents. And the first way that we deal with this, or we find the applications, is we learn about how to compound things annually. So the most regular thing that we talk about compounding annually is money. But then there's also population growth and decrease of values of cars. So what these generally are involved in, compounding annually means every year they add the interest on. So every year you're going to get whatever interest that you made on a loan or on money, like the bank pays you, you get it added into your account once a year. So that's what compounded annually means. So this is the general formula. A of t just means it's a function of time. This A changes. It's not always A. Like over here it's K. It can be any letter here. But this parentheses doesn't mean multiply. It means it's a function of time. Okay, so that means you're going to be given mostly all of these pieces when you're writing these formulas. But T is the thing that really affects the problem. And it's an exponential, just like, we've been doing. Okay, so P is the principal amount, or the initial amount. We also call it the principal. Principal. Okay, also all these things are going to be given to you. The rate, that's your percent rate of change. You always put that in as a decimal. And you'll notice that here we have the plus and the minus. Remember, that's a shortcut to say we're going to add to R, 1 to R, or subtract R from 1. So if I add R, or if I add the percentage rate, that means I have a whole plus a percent. So that means I'm going to be increasing, or it's a growth problem. If I do 1 minus R, I'm going to be taking away from that initial. So the whole thing is 100% or 1, and I'm going to take away that percent, so that's a decay. So down here, if you break apart the pieces of a formula, what is the initial amount? So sometimes they give you the formula just here, and they say, okay, is that a growth or decay? Now we've seen these before. You know that number right there is a decimal. It's less than 1, so it is a decay. What is the initial amount invested? Well, that's the thing that you multiply the exponential by. So that's 3,500. So that could be 3,500 people, $3,500. But that's the initial amount put into whatever is going to have some sort of percentage rate. And then what is the annual percent rate of change? Well, I know that this is a decay problem. So I know to find 0.78, this number right here, I had to do 1 minus R. Okay, because that's the formula that we have up here. I know this is, it feels like I'm going really slow and annoying you, but it's important that you understand that up here, 1 minus R was a decay. So since we decided this was a decay problem, I know that to get this number right here, I had to do 1 minus R. So then, to figure out what R is, I subtract, and I get negative 0.22 is negative R, and then divide by that negative 1, and I get 0.22 as my rate. So that is 22%. So it's going down 22% per year. So over here, this formula, growth or decay, well, you look at this number right here, that's a big number, bigger than 1. So it's going to be a growth. What is the initial amount invested? That's it right here, 2,735. And then what is the percent rate of change? Well, since we decided it was a growth, we know that it's 1 plus R to get that number 1.35. So I just simply subtract 1, and R is 0.35, or 35%. Okay, to find the actual percent rate of change, you have to think about it in terms of 1 plus that rate or 1 minus that rate. Okay, so to actually use the formula, instead of just looking at examples of it, you think of, in terms of, like, say, bought a new car. Someone bought a new car, and the moment you take it off the lot and you've bought it, it starts losing its value. So since it's losing its value, it depreciates its value. It's going down. That means this is a decay problem. So that means the formula that we're going to be using is P A of t equals P times 1 minus the rate to the t power. So the formula is A of t, the initial amount he paid, the initial amount that it's worth, and then 1 minus, so I have to subtract the rate. Now it's 7%, but remember, you either divide that by 100 to get 0.07, or you move the decimal place over 2, whatever, way you want to deal with it, to the t power. So the actual formula is 35,000. 1 minus 0.07, so that's 0.93 to the t power. So there's a few ways we use this. The first way is we're just going to plug stuff in, so 5 years. So if I want to figure out how much is left after, how much it's worth after 5 years, I'm going to put 5 years in for my t. So t is the time, and every 5 years it's going to depreciate 7%. So I just plug that in. And it doesn't say it here, but it should. I'm going to say to the nearest $100. I'm not going to say that my car is worth $357.52. Okay, I'm going to get close. So it's $24,349 and 9-ish cents. Okay, to the nearest $100. So this is the 100 spot. So this is the spot that I'm rounding to. So it's 24. That's to the nearest $100. The last question that we generally ask, or one of the questions that gets asked, is to ask for time. So right now we haven't really done anything that relates to this exponent t. But they want to know when to the nearest year will Dave's car be worth $10,000. So that's this amount. That's the final amount. So $10,000 goes in for that. Okay? And what we don't know this time is the t. So this is where all of our work in solving exponentials and all that stuff comes in. So this is, we just solve it then. I'm just going to move it down a little. So we divide by, we have to isolate the exponential. Okay, and we get some nice big number. Not, well, actually, it's a small number. Okay, don't round, or if you do, take it really far in. So we're going to log both sides. Remember, this t comes out in front. So I have the log of this mess. Leave it in your calculator if, excuse me, I can't talk and write at the same time. I guess it's a problem. Leave it in your calculator and just use the answer instead of retyping it in. It's an important thing that you should learn when dealing with your calculator. So when we're done here, what we get is 17.26, and it's said to the nearest year, so it's 17 years. So if he keeps his car 17 years, it'll only be worth $10,000, which really isn't that bad for a 17-year-old car. All right, see ya.